Alright, so when it comes to working problems out using vectors algebraically, let's see how this goes down. So for this problem, we need to write an ordered pair that represents the vector from point x, going from negative 3, 5 to point y, which is at 4, negative 2. And then they also want us to find the magnitude of vector xy. So how we're going to go about doing this is first let's just get a mental image of where these points are going and which direction this vector is going. If you're having trouble imagining it, then why not just graph the points? And so if we were to graph those points, we'd have something that looks like this, now wouldn't we? If we were going from negative 3, 5 to 4, negative 2. So notice the direction of this vector is going down and to the right. So when you're trying to give the ordered pair here, and by the way, when we're talking about the ordered pair here, is we want to put those in component form. Let's note what happens here going from point x, which would be the start, to point y, which would be the finish. So let's first grab the horizontal component. One thing that's very, very important to note here, that when I'm putting in these components, is always start from the origin point and always work your way towards the tip of the vector. So notice that in the direction that I went here, going from the start to finish, I had to go to the right to get directly below the tip of that vector there. So if I'm going to the right, that means I traveled a distance here of positive 7. Now let's fill in the vertical vector. Now notice that the vertical component here is actually going downwards. And because this vector is going downwards, we need to represent that with a vertical component of negative 7. So one way that we can get these components here for this ordered pair would be just to simply draw it. And so now we have our components here. Use the pointy parentheses there, and our horizontal component was positive 7 and our vertical component was negative 7. So that's all they're asking you for when they say write the ordered pair. Okay? If you want to approach it from more of a calculation standpoint without making a picture, realize that you have to look at the points and realize that you start here and you finish there. So when you're trying to find your horizontal change, the horizontal change needs to stem from the start and go to the finish. So when you're trying to find the difference, you need to start with this 4 here, and you need to subtract the other x value right here to find that change. Because if we're going from negative 3 to positive 4, that means we had a total change here of positive 7. We added 7 to go from negative 3 to positive 4. Maybe you can play the same number logic here. If you're going from 5 to negative 2, what direction do you go in? And if you do that, now you've just found your vertical change. Going from 5 to negative 2, which would involve us taking a negative 2 and subtracting 5, that gives us a change in negative 7. So realize there's our horizontal change of positive 7, there's our vertical change of negative 7. So there's two ways you can go about doing it. Now when it comes to finding the magnitude of that vector, the magnitude of vector xy is just asking you how long is it from tail to tip, right there. Realize when you have it in graphical form like this, you've just made yourself a right triangle. So now it just boils down to Pythagorean theorem. Realize that's your horizontal change and that's your vertical change right there. So realize you're just dealing with two legs in your right triangle. In fact, every single time you have a vector in component form, like we have it here, to find the magnitude, we're always going to use the Pythagorean theorem. So a squared plus b squared equals c squared, which is our magnitude. So, which would be this value right here. So if we square all both those numbers, we'll get 98, because 49 plus 49 would give us 98. But then don't forget, to find our magnitude, we have to take the square root here of 98, which, if you just recall, we got 98 from doing 49 times 2, which boils down to 7 square roots of 2. Another way you can notice is that you were dealing with the 45, 45, 90 right triangle, because these two side lengths are the same. So remember that length right there has got to be 7 square roots of 2, regardless. And so there would be your magnitude, right there. So we found the vector in component form, and we found the magnitude. So to sum this up, right over here, explain how to find the magnitude of a vector when it's in component form. Well, whenever you're being asked to find the magnitude of a vector when it's in component form, what they're talking about is something like this. It's very simple to find the magnitude. We just realize that the magnitude, which can be, call it c, I suppose, we can say that a squared plus b squared equals c squared. In other words, we're using the Pythagorean theorem. So then one important question that you're going to be able to figure out by the end of this unit is how you can figure out the direction of the vector when it's in component form. So going back over here, and we saw that we had this vector going in this direction. Well, it's no surprise what the direction is, but actually 45 degrees is a little bit misleading. Remember, when you're trying to find the direction of the vector, if you remember from the last section that we worked on here, is that you need to figure out the direction in this fashion here. So you'd call that direction, oh, you can call it one of two things. You can either call it, 315 degrees, or you probably could call it negative 45 degrees. I'll let you get away with that. But how could we nail down the direction if it wasn't just a perfect 45, 45, 90 right triangle? Well, let's see here. If we knew this side, and we knew this side, and we were trying to figure out this angle right here, what back in our other trig sections did we use to help figure this out? We have the opposite side, and we have the adjacent side, don't we? So to figure out that angle, you guessed it, it's tangent time. So if we had this in component form, so once again we have A and B, a horizontal and a vertical component. When we're trying to find the direction here, suppose we'd set it up just like this, right? The tangent of our angle would be equal to opposite over adjacent. Now in this case, which one would be the opposite? Shouldn't it be the B, because that's our vertical component with that angle? Yeah, it's going to be B over A every single time. It's always going to be that vertical component over that horizontal component. But we can go one step further with this, right? Because this isn't our angle right here, that's just our ratio. So to solve for theta and get theta by itself, what we have to use here is inverse tangent. So we're back to that again. So eventually we'll get there. We'll take a look at that in a sample problem here in a little bit.